think we're ready to get started whenever you're ready.
Okay, great. Yeah, so welcome back. So today we'll continue talking about generalization guarantees, specifically sample complexity for classic supervised classification. So this is the introductory background. And as I mentioned, next time we'll talk about active and distributed learning, which are really topics more relevant for learning in the age of big data. Okay, but today we'll finish the discussion about sample complexity in traditional machine learning for supervised classification. Okay, so again, we'll be thinking about supervised classifications where all the examples will be labeled. So for example, emails might be labeled as spam or not spam if you want to do spam detection. And we will be thinking about the formalization that we introduced last time, namely the distributional model for supervised classification as captured by the PAC and statistical learning theory models. Okay, and as we've seen last time, in these models, we assume that we have some instance space, and we have a distribution. So a distribution over the instance space. This is a distribution from which it's a fixed unknown distribution, and both the training examples and the test examples will come from this distribution. So at the training time, we're going to see a sample S of examples x1, x2, xm that are drawn IID from this distribution, so independent identically distributed from this distribution, and they're also going to be labeled according to some fixed unknown target function, which will denote here C star. Okay, and then our goal is to find some, to do some optimization over the given sample, and to find the hypothesis H, or a classifier H, and we want our classifier to have small error rate with respect to this fixed unknown distribution and the fixed unknown target function C star, right? And again, the notion of error rate that we're using here is the classic zero-on loss or classification loss, which is just simply saying the error rate of the true error rate of a hypothesis H or of a classifier H with respect to this unknown distribution D and the unknown target function C star is just the probability that my hypothesis H predicts differently from the target function on an example drawn at random from C star. So that's the goal, and to find a classifier that has true or a hypothesis that has true a small true error rate. And as we discussed last time, to achieve this goal, we need to inject some additional bias to the learning problem. So what we're going to do in these classic frameworks, we're going to fix a search space, hypothesis space H, and we'll really try to compete with the best function, the best classifier from this fixed hypothesis space H. And we want that the complexity of this hypothesis space is not too large. And now there are two cases. In the realizable case, we believe that the target function truly belongs to the search space H. So in this case, our modeling is perfect. We totally correctly guess the type of the form of the target function. That's nice for the kind of theoretical simplicity for mathematical convenience. Now, of course, more relevant in practice is the agnostic case, where we don't assume that the target function, unknown target function, really belongs to the search space H, but we assume it is somehow close to the search space, and we're then just computing the best function in H, right? So, yeah. So this is the agnostic case. So there are the realizable cases and the agnostic case. And as discussed yesterday, the challenge is kind of in this, when we do machine learning, is that we really want to find a classifier that has small true error rate, right? So according to this notion of error that I just reminded you about, but the problem is that we cannot measure the true error rate, and we instead can only measure the empirical error rate, the training error rate, right? So on the given sample, for any hypothesis H, we can go and measure the empirical error rate, but not the true error rate. And so that's kind of the challenge, because we want to find hypothesis with true error rate, hypothesis has small true error rate, but we can only measure the empirical error rate. But luckily, there are these generalization guarantees or sample complexity bounds that help us bound kind of uniformly for all classifiers in our search space this sample complexity can help us bound the true error rate in terms of the empirical error rate. Right, and this is what we've been discussing last time, and we proved the sample complexity bound. So we went for the proof of a sample complexity bound for the simple case that really applies in the simple case where the target function truly belongs to the search space H, so really applies to realizable case, and also to the simple case where the search space is finite. So H is a finite set of classifiers. Okay, and so to recap, just to remind you the form of the bound. So what we proved is the following. So if H is finite, we show that if in the training phase we see this many labeled examples, this many being 1 over epsilon times log size of H plus log 1 over delta labeled examples, when these many examples are sufficient so that we can guarantee that with high probability over the draw of the training samples, we have it uniformly for all classifiers, for all hypotheses in our search space. We have it uniformly for all such classifiers. If our true error rate is at least epsilon, so if there are bad classifiers because their true error rate is too high, is at least epsilon, then these classifiers will definitely make at least 1 error over the training set. So meaning their empirical error rate will be strictly greater than 0. So we'll be able to detect them over the given training set of examples. Okay, and as we discussed, the consequence of this is that this bound really, consequence of this bound is that if we're in the realizable case, so if the target function C star truly belongs to our search space, and if we have a kind of a consistent learner, that means an algorithm that is able to find a classifier that is perfectly consistent with the training sample, so correctly classifies the training samples, then the training set of examples, then what this bound tells us that only this many labeled examples are sufficient so that we can guarantee that our consistent learner, so is able to output a classifier that has generalization error, true error at most epsilon with high probability at least 1 minus delta. Okay, so that's a consequence of this sample complexity bound that we proved last time. So in this very simple case where H is finite, and if we're in the realizable case where the target function truly belongs to our search space, then what this bound tells us is that these many labeled examples are sufficient so that with high probability over the drop the training set of examples, the classifier that our consistent learner outputs has true error or generalization error at most epsilon. So that means we are good. We're going to learn a good classifier that generalizes. Okay, so this is what we proved last time. One comment that I didn't get a chance. Oh, and just let me mention here. So here, notice that the bound is logarithmic in size of H. That's why it's a good bound. It's also linear in 1 over epsilon. So the dependence on 1 over epsilon is linear. The dependence on size of H is logarithmic. And as I mentioned, also the dependence on delta is also very small. It's only log 1 over delta. Okay. And one thing I didn't get a chance to mention last time, so if you look at this form of this bound, demystifies the word PAC, because I use the PAC model. What does PAC stands for? It stands for probably approximately correct, right? So if I say in English what this bound says is that if I see these many labeled examples, and if I use a consistent learner, then with high probability at least 1 minus delta will be approximately correct because our error would be at most epsilon. Right, and this is where the name of the PAC model comes from this simple bound. Right, so again, basically what the bound tells me, if I see these many labeled examples, if the target function belongs to the search space, and if I have a consistent learner that is able to output a classifier that is perfect, but perfectly correctly gets classifies a training set of examples, then I know that these many labeled examples are sufficient so that I'm confident that my consistent learner outputs a classifier that has true error rate at most epsilon with high probability at least 1 minus delta. So again, with high probability, at least 1 minus delta will be approximately correct. So meaning the generalization error will be at most epsilon. And again, this is where the name comes from, stands for probably approximately correct. Okay, and this model was introduced in the computer science literature by Les Valiant in the 80s, and it really just formalizes what I just said. You know, if we're in this distributional learning setting, we say that an algorithm A, PAC learns a concept class H, if for any target function C star in H, for any, this is of course fixed unknown target function C star in H, for any fixed unknown distribution D over the instance space, we have it for any epsilon and delta. My algorithm A uses only a number of samples that is polynomial in the relevant parameters, and also uses only polynomial running time. And then with high probability, at least one minus delta, my algorithm A produces a classifier in the search space H that has error at most epsilon. This should be here at most epsilon, right? So my algorithm runs in polynomial time and is really output some high probability, produces a classifier that has error at most epsilon. That means is probably approximately correct. Yes, and just to point out also, right, there is one more requirement that I don't talk very much explicitly in the lecture, which is that the algorithm runs in polynomial time. And by polynomial, we mean polynomial the relevant parameters. What are the relevant parameters here is the dimension of the problem, the description length of the input, 1 over epsilon, 1 over delta, and the size of the target function. Yeah. And recall again, like we went through this slowly yesterday. What is epsilon? You know, it is this error parameter, and delta is the probability of failure. Yeah. Right. So really, the major difference between the statistical learning theory framework, Vavnik, and the PAC model of Valiant is that really in the PAC model, we also impose that our algorithm also runs in polynomial time. Because Les Valiant himself was a computer scientist, so he also was interested in polynomial time. But in both models, we really want to output classifiers that with high probability are approximately correct. Okay, and this hopefully answers a question that was there yesterday, because somebody asked me yesterday, what is the PAC model? And this is the precise definition of the PAC model, which is easily motivated once you see the form of the bound that we can prove in the simple realizable case. Okay, and actually I want to make one more comment. So again, we've seen this bound by now several times, yesterday and today. So in this simple case, where we are in the realizable case, the target function truly belongs to the search space, and the search space is finite, so we have only a finite number of hypotheses, like, you know, maybe the class of conjunctions, the class of disjunctions, the class of decision trees over the Boolean QVs are examples. So in this case, we can get this type of bound. And there are really two ways of writing this bound. So so far, I kind of wrote it in the PAC sense, in this PAC sense. And in this PAC sense, we really write it in a way that looks like the way you've seen it, which is we talk about how many examples suffice to guarantee small error with high probability, right? And we've seen this by now. You know, we say if the number of samples we see in the training phase is like 1 over epsilon log size of H plus log 1 over delta, then these many labeled examples are sufficient so that with high probability, at least 1 minus delta, we have a Q uniformly for all classifiers. If there are bad classifiers over the underlying distribution, if our true error rate is at least epsilon, we will be able to detect that over the sample because they'll make mistakes over the samples. Okay, or another way of writing it by the contrapositive, which I mentioned yesterday, is that these many labeled examples are sufficient so that with high probability, at least 1 minus delta, we have it uniformly for all classifiers in the search space. If any such classifier has a theoretical error rate 0, perfectly correctly classifies the samples, where true error rate is at most epsilon. So they generalize. Okay, so this is one way to write the bound. And again, in this form, really, we talk about how many examples suffice to guarantee a small error with high probability. But actually there is, and this is really more the PAC way of writing the bound. But there is really another equivalent way, which is what I call a statistical learning theory way. So the people from statistical learning theory like to write it this way. Here we are just writing the bound a bit differently. It's just really very equivalent bounds. So it's just a rearrangement of the previous form of the bound. So here we're just saying, well, no matter what is the number of samples, I want to know how I can upper bound the uniformly for all functions in my concept space. How can I upper bound their true error rate as a function of the empirical error rate? This is in general. In this case, for the realizable case, based on this bound that we looked at, basically a consequence of bound number 1 written on the slide here is the following. and I'm going to go through this slowly. So this is the statistical learning way of writing it, and this is as follows. So we are saying for any number of samples m, what we can show is that with high probability at least one minus delta, we have that for all classifiers H in my search space that have empirical error rate 0, so perfectly correctly classify the samples, for all such classifiers will have it where true error rate is upper bounded by 1 over m times log size of H plus log 1 over delta. Okay, and how do I get this bound from the previous bound? Well, I just substitute, so I can just epsilon here is kind of the generalization error, and I solve for it. And so then if I just solve for what is epsilon as a function of m and log size of H and log 1 over delta, this is exactly what I get here, the bound at the bottom. Right, so basically this tells me that no matter the number of samples, and no matter the number of training samples m is, we can prove it with high probability, at least 1 minus delta. We have it for all classifiers H in my search space. If they are perfect over the sample, if we make no mistakes over the sample, then we have the true error rate, the generalization error can be overbounded by 1 over m, log size of H plus log 1 over delta. Yes, so in other words, you see that the generalization error quickly basically decreases with the number of samples. So it's like 1 over m, and then times the complexity term. So this is log size of H is really the complexity term here. Okay, and these are really so it's kind of good, right? This is good. The decay here is very good. And so, and these are really two ways I kind of equivalent ways to write the bounds. It's just different people from different communities like to write it a bit differently. Okay, and one thing to remember from the first bound here is that here the dependence is in the PAC way of writing it. The dependence in the realizable case is linear in 1 over epsilon. And also in the statistical way of learning, a way of writing the bound, again, the error rate, the true error rate, the upper bound and the true error rate again quickly decreases, and the decrease here, the functional dependence on m is like 1 over m, so it's linear in 1 over m. Okay. So any questions at this point, I guess? So if there are no questions, I guess I can move on. And just also quickly mention what I talked about last time, what I briefly mentioned last time. So this, so far the discussion is only for the realizable case. How about the agnostic case, where we are not guaranteed that the target function belongs to the search space, and as a consequence, we are not guaranteed that we'll be able to find like a classifier that has that is perfect over the training set of examples. So this is really the most realistic one in practice. So in that case, luckily, we can also get similar sample complexity bounds. Just the form is a little bit different, but they look very similar. So here, what we can say is that if the number of training samples is of the order now 1 over epsilon squared times log size of H plus log 1 over delta, then these many samples are sufficient so that with high probability, at least 1 minus delta, we have it uniformly for all classifiers in the search space, where true error rate is only within epsilon at the empirical error rate. Yeah, so we've seen enough examples, so then basically we get this uniform convergence, uniformly for all classifiers in the search space, where true error rate is very close to their empirical error rate. So therefore, that means if I do this, I use this algorithm, empirical risk minimization, and if I just find a classifier that has a smaller training error, like maybe the smallest training error over the sample, then I'm guaranteed that the classifier with the output competes with the best classifier in my search space H with respect to this fixed unknown distribution. So then I really achieve the best I can hope for. And again, here, because we are getting a stronger stemma than in the realizable case, now we get that for all classifiers, no matter how good or bad they are, where true error rate is within epsilon of the empirical error rate in high probability. Because of this, now the dependence on epsilon is 1 over epsilon squared. So it's as opposed to 1 over epsilon as for the realizable case. So I need a few more samples for this, but still not too many. Okay, so this is the bound for the agnostic case. And turns out you can again also write this bound for the agnostic case. So this is more the way we have it right now is again the PAC way of writing the bound. How many samples do you need so that you can guarantee that with high probability this uniform convergence statement happens? This is more the hack way of writing the bound. But there is also an equivalent, literally just an equivalent, just a rewriting of the equations, equivalent to what we call statistical and inference style way of writing the bound, which is here at the bottom. And again, the bound, as we did for the realizable case, the bound in this case has the following significance. So what we can show here is that no matter how many training samples we have, so if we have m training samples, so m here is the number of training samples, but we can show that with high probability, at least minus delta, we have it uniformly for all classifiers H in my search space. I can upper bound the true error rate as a function of the empirical error rate plus some term, this term over here, that looks like square root of 1 over 2m, roughly speaking, times log size of H, right? So I can upper bound the true error rate by the empirical error rate plus this term that decays as I see more and more, goes to 0 as I see more and more samples, right? So I can do this uniformly for all classifiers in the search space. So this is kind of pretty remarkable here. So uniform for all classifiers in the search space. I have it to have probability uniform for all classifiers in the search space. The true error rate can be upper bounded by the empirical error rate plus a term. It looks like square root of 1 over m log size of H, roughly speaking. And this term goes to 0 as m gets large. And
it's a
yes.
couple.
So Nina, I'm confused. I thought the agnostic case meant that the hypothesis didn't have to be in the assumed hypothesis space, but close. So I don't quite see.
Yeah. So yeah.
I don't quite see why this is agnostic.
Yeah. So here is what I'm saying is the target function, the function that labels my example, doesn't have to belong to the hypothesis space, but the function that the algorithm will output will still be in form of fixed hypothesis space. And then the guarantee that I'm giving is only for functions in this fixed hypothesis space, then I can bound the true error rate as a function of the empirical error rate.
Okay, all right, thank you.
So like, right. So and then what I can do, so if the target function doesn't belong to the search space capital H, but but the algorithm only output classifiers from the search space, and then what I can guarantee mathematically as a consequence of this bound is that if I do empirical risk minimization, if I find a classifier from or a hypothesis from the search space that has the smallest error rate or over the sample, then the consequence is that my algorithm competes with the best classifier from this fixed search space. So if the target function doesn't belong to the search space, then it means that the best classifier from the search space might not have, of course, true error rate 0, right? Because the target function doesn't belong to the search space. There is no classifier in the search space H that is perfect because the target function doesn't belong there. But then what I'm going to do, I'm going to still, my classifier will still output, my algorithm will still output only a classifier from that search space. But at least as a consequence of this bound, I'll be guaranteed that the classifier that the algorithm will output will be will have true error rate that is comparable to the best error rate, to the error rate of the best classifier from this search space.
Okay.
So I'm not going to, in the agnostic case, I'm not going to be guaranteed to output a classifier that has very error rate that goes to 0, but at least I'm going to be able to guarantee that I'll output a classifier whose error rate competes with the best error rate from this search space.
Another question.
I think I have a very related question. So I was thinking, can we think of the realizable case as sort of a limit of the agnostic case, and if so, can we use this theorem for the agnostic case and like say substitute error of the classifier? Like if we do find a classifier that has perfect that has a perfect classification on the training set, then do we actually get 1 over epsilon square? I was just thinking, does this theorem sort of also subsume like the previous theorem that we saw?
So well, it subsumes it, but if we are in the realizable case, if we know that the target function does belong to the search space, then we can get a better bound, right? So in the realizable case, we get a dependence. If I promise you that the target function does belong to the search space H, then you only need to see 1 over epsilon log size of H samples, for example, to learn well, because then you are guaranteed that there will be a classifier that is perfect over the sample, and then you guarantee that the classifier will have true error rate at most epsilon. So if the target function truly belongs to the search space, you can get an improved dependence on 1 over epsilon.
Okay.
Right here in the agnostic case, the dependence is 1 over epsilon squared, because here we kind of roughly speaking, we also worry in this bound here, this bound is stronger than what we had for the realizable case, right? If I go back to the realizable case, all we promise is that all classifiers that have empirical error rate 0 have true error rate at most epsilon if we see this many samples, 1 over epsilon log size of H samples. But I never tell you anything about classifiers that don't do perfectly over the samples here, right? But I only need a smaller number of samples, only 1 over epsilon samples. Now in the agnostic case, which is bound here, I need more samples, but then I promise you something stronger. I promise you that for all, uniformly for all classifiers that have good or bad empirical error rate, where true error rate is within epsilon of the empirical error rate.
Okay.
Yeah, so I guess you can think of the bound, yeah, the bound for the agnostic case does subsume the bound for the realizable case, but it's not what I want. If I am in the realizable case, and if I'm in the realizable case, I want to use the bound for the realizable case because I can learn with fewer samples.
Thank you.
Yeah.
Is there a weaker assumption that you can make so that you get a 1 over epsilon for the agnostic case?
So here, I guess right now I'm just looking at, I'm staying for simplicity 2 of these classic models of the realizable and agnostic case, but there are more refined. So I'm not assuming anything about the noise here somehow. You can also start talking about the noise. And there are various noise conditions like Massard noise, where maybe the label is flipped with a certain probability, constant probability, or Zibakov noise. So there are various, there are various kind of noise ranges in between realizable and agnostic, and there you can get closer. For example, for Massard noise, you can get a bound. You still arrive some noise, and you can get roughly speaking 1 over epsilon dependence in the number of samples. Yeah. So there is a whole theory around this statistical learning theory. To interpolate between the agnostic and the realizable case. One concrete example is the so-called Massard noise, and there the bound really looks closer to 1 over epsilon, but you still allow some noise. So you're not quite in the realizable case. Yeah, so there is huge amounts of research in this, I guess, yeah, in this setting. So here I'm kind of presenting the most basic models. Okay. Great. So but so far I still have the realizable, sorry, as far I still have the finite hypothesis space case. So it's still finite, right? And so, right. And so, yeah, still finite. Just a quick note, actually, I've already mentioned this. So in the PAC model, in the agnostic case, the difference is 1 over epsilon square dependence as opposed to 1 over epsilon for the realizable case. And in statistical learning theory style way, is like square root of 1 over m decay on this term that goes to 0 as opposed to 1 over m decay. Yeah, but of course here in both cases we still have the complexity term that comes into the bound log size of H, right? So it depends on the search space, the size of the search space, how many samples do I need to get kind of these nice bounds. But and so far, because we are talking about finite a set of functions, you know, the complexity here measure that we are using is log size of H, so log of the number of classifiers in our search space. But you know, in most in many of the examples that people care about in machine learning, you know, H is not finite. So for example, so how does the bound look like when H is not finite? What can we say then? You know, can we get similar nice bounds? And basically, yeah, so what if, for example, H is a class of linear separators in RD, right? Of course, when we have infinite number of such, we have infinitely many such linear separators. And so then how do the bound look like? So actually here on this slide, I have a few examples of classes of functions that are infinite. Just let me quickly go through them. So first of all, linear separators that we've seen last time. And these are, of course, relevant for practical machine learning, but I also have a couple of other quick examples here that I'm going to use for describing the notion of BC dimension. And besides the class of thresholds on the real line. So here I just have each example, I just has one feature, and then the classifiers look very simple. I just pick a threshold, you know, and I classify all the points to the left of the threshold as negative and all the points to the right of the threshold as positive. Okay, and or another example here is a class of intervals on the real line. Again, all the examples just have one real value features, and then what I do, I pick a couple of, I just basically pick an interval, 2 endpoints A and B, and classify all the points inside the interval as positive, and all the points outside the interval as negative. Okay, so what can we say then? And turns out we can get equally cool results. We just have to replace the log size of H with a relevant measure of complexity. And to get some intuition, let me walk you through a couple of these examples. So why we are able to do so. So even if the class of functions is infinite, at a very, very high level speaking, we really care about the effective number of hypotheses that are realizable over a given sample of a given set of M examples. And so I'm going to introduce this notation, which is called the shattering coefficient. So if H is my set of classifiers, I'm going to denote by, and S is a set of examples. I'm going to denote by H of S, the set of all possible labelings of my data set using classifiers from the search space H, from the hypothesis space H. Okay, so it's H of S. So S is again a training set of examples, and H is a set of classifiers, say maybe linear separators. I'm gonna know by H of S the set of all possible labelings of my set S using concepts from H. And for concreteness and for simplicity today, let's assume that H is a set of binary classifiers. Only plus minus 1 labelings are allowed. Okay, and I'm going to know by H of M the maximum number of ways of labeling M points using concepts from my search space H. Okay, so just to, and because H is actually a class of binary classifiers, H of M is equal to the M, because you know the label of any single point can be plus or minus. Okay, so just to give an example, a quick example to instantiate this concept. So if H, the set of classifiers we're looking at, is just the set of thresholds on the real line. Now, of course, there are infinitely many thresholds, you know, that I could have on the real line, but infinitely many classifiers. But you know, for any given 4 points, you know, I don't have too many labelings of these 4 points with thresholds. And in particular, if these are my 4 points, right? If these are my 4 examples here, right? This point, so these are maybe my examples, example 1, example 2, example 3, and example 4. But of course, on these 4 points, you know, like these 2 thresholds, even if they have different thresholds, right? This threshold here and this classifier here and this classifier here, they are really 2 different classifiers, 2 different thresholds, but they really induce the exact same labeling on these 4 points. They induce a labeling minus, minus, and yeah, the first 3 points are labeled as minus, so minus, 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 and plus. Right, both of these thresholds label these 4 points in the exact same way. Okay, that's the first observation. So in the end, on any given set of points, you know, I don't have too many labelings with thresholds. And actually, how many labelings do we even have on these 4 points here with thresholds? So yeah, how many labelings can we achieve with threshold on these 4 points? Maybe somebody can volunteer to mention. 5, precisely 5, perfect, right? Because why? Because these are the 5, like depends, I have 5, right? I mean, I can put the threshold in the first segment here, or in the second segment here, on the third segment here, the fourth segment here, fifth segment here. I have basically 5 different places where I can put the threshold to produce a different labeling, right? And these are the labelings I can obtain using thresholds on these 4 points, right? And in general, if I have M points, if I have M distinct points, and they're all distinct, then the number of labelings that I can achieve with thresholds, the number of labelings at this point I can achieve with thresholds is only M plus 1, right? Which is of course much smaller than 2 to the M, the number of possible labelings achievable in principle, right? If I use any type of classifier, right? So you know, and this makes sense because this class of kind of thresholds is a very simple class of functions. So you know. And indeed, the effective number of hypotheses or the effective number of labelings being used over M points is only M plus 1, much smaller than 2 to the M. So this is for the case of thresholds. Now, if we are doing, say, another quick example, the case of intervals, where again, what we do, we pick an interval with the classifiers look like this. Again, the features, the examples only are represented by 1 real values feature. And what I do, I just pick an interval really on the real line, and I label all the points inside as positive and all the points outside as negative. And again, I claim here that h of m, the maximum number of labelings and points by using intervals is much smaller than 2 to the m. Now it will be roughly speaking m squared. Why? Right, m squared, right, precisely. And so I guess, and why? Because, you know, in general, like if size of S, if I have m points and they're all distinct, say, you can easily show that the number of labelings of these m points using intervals is like m squared, right? Because why? Because if I'm trying to label, if I'm thinking about achieving a labeling where at least one point is positive, well, then there will be m plus 1 options for the first part of the interval. There are m options left for the second part of the interval. The order doesn't matter. So really, I get, roughly speaking, m plus 1 choose 2 possible labelings, or at least one of them, the point is positive, and then I get plus 1 for the case where the labeling is negative, because I can always pick both endpoints to be in the same interval, and then I get, or in the same part here, and then I get also the empty interval, which leads to all negative labeling. So basically, to summarize here, if I'm looking at the intervals on the real line, and if I have endpoints, the maximum number of labelings of those endpoints by using intervals is only m squared, you know, which is again much smaller than 2 to the m, which is the number of possible labelings I could achieve of those endpoints if I allow the set of classifiers to be kind of arbitrarily complex. Okay, so so this is a bit higher than the number of labelings I can achieve with threshold, which is only m, but still is much smaller than 2 to the m. It's only m squared. Okay, and hopefully with this, this shows that somehow kind of the that maybe a relevant notion of complexity should really be this shattering coefficient, which is the maximum number of ways of labeling endpoints using concepts from our constant space. Maybe this would be a more relevant notion of complexity as opposed to size of h, which in this case would be infinite. Okay, cool. And actually, one more comment before I go to a bound to show a bound. So actually, now that we have this notation, we're going to say that a hypothesis space H shatters the set S if basically I can achieve all possible labelings of the set S using classifiers from H, right? So this is the definition. So in the case where I can indeed achieve all the possible labelings on a set S using classifiers from H, then I say that the set H shatters labels in all possible ways the set S. Okay, cool. Now this discussion, so something very interesting, but I'm not going to have time to prove here. It takes a lecture in a learning theory course to prove it. But it turns out that, like, indeed, so like, hopefully I try to give some intuition of why this shattering coefficient, which is the maximum number of ways of labeling endpoints using concept from the concept space, is kind of a more relevant notion of dimension or complexity of a hypothesis space H. If you are dealing with infinite with sets of classifiers, if you are dealing with an infinite search space, and indeed, actually, it turns out you can prove, and this is non-trivial now, that will become the math is not as trivial as we've seen last time. So it turns out that you can prove the following: you can basically prove a bound that is very similar to the bound that we've seen for the case when the class of functions is finite, right? But actually, and instead, what we do, we replace size of H with, roughly speaking, with log of the shattering coefficient, right? So when M was fine, when H was finite, we had a bound that looked like if the number of samples I see in the training phase satisfies like is at least 1 over epsilon log size of H plus log 1 over delta, then with high probability some good event happens. Now it turns out that actually you can also prove if H is infinite, you can prove that you can replace size of H with basically the shattering coefficient at roughly speaking level n. So we can show the following. So if for any class hypothesis class H, for any distribution D, for any target function C star, if the number of labeled examples we see in the training phase satisfies this inequality, M is greater than, roughly speaking, 1 over epsilon log of the shattering coefficient at a level 2m plus log 1 over delta, then that's sufficient so that in high probability, we have it uniformly for all classifiers. If they are bad classifiers, then their empirical error rate will be strictly greater than 0. Okay, so basically, essentially, what we can do here, we can replace size of H with the shattering coefficient. So this term here, roughly speaking, but the major change. There's some also change in the constants, but those are minor. Really, the major change here was size of H was replaced with H of 2m, which is really the maximum number of ways of labeling 2m points using concepts from our concept space. Okay, now the proof of this statement, so it's again non-trivial, implies involves two probabilistic tricks, double sample argument and Rademacher argument. So it's non-trivial, so I don't have time to go through it. But turns out you can get it, so it's a very interesting proof there. You can get it, but the issue is that in this form, the bound itself is still not very easy to use. Why? Because it's not easy to interpret, and sometimes it's hard to calculate exactly. Why? Because we have basically both of these sides of the inequalities depend on m, right? So here m is, I'm saying if m is at least 1 over epsilon log of h of 2m, roughly speaking, then some good event happens with high probability. But what is h of m, for example? We computed it for intervals was m squared, roughly speaking, or for thresholds it was m, right? So I would always have to solve an inequality here to get how many samples do I need to to get generalization. I'd have to solve an inequality that looks like m is greater than 1 over epsilon log of m squared, for example, for intervals, right? So it's not, I still have to go to some further calculations.
There's
So
a
that's one. Yes.
So in the statement of the theorem, I think there's a word missing or something. If the number of labeled examples seen m, what is that? Seen is m or something?
The number of examples seen, examples m satisfies. Yeah, maybe it's a type. Yeah, maybe the number of labeled examples m satisfies what we have seen. I guess that's the meaning. If the number of examples we have seen.
The number of examples is m?
Yeah.
Yes.
Okay.
Yeah, that's what it says.
Okay, great. All right, thank you.
Yeah. That, yeah, I guess the meaning, yeah, the number of examples we've seen. Yeah.
Okay.
Right. So in this, so again, like the issue with this statement here is, is basically the bound itself contains m on both sides of the inequality, and number one, and number two also maybe doesn't give us like an easy intuition when learnability is possible, and in particular, like for example, a case that wouldn't be good in the worst case if h is very complex and contains but I guess it's still a meaningful bound, because, for example, it does tell us that I guess if h is very complex and it contains all the functions in the world, then h of m is 2 to the m, and so then this bound will be kind of not achievable, right? Because it tells us if m is greater than m over epsilon times some terms, then some good event happens. Of course, this will never happen. So yeah, I guess it's a good intermediate bound. That's what I'm trying to say. And it turns out that actually we can clean it up, and we can upper bound. Turns out that there is a notion of a complexity measure called VC dimension that can be used to upper bound this shattering coefficient, and then to clean the bound out, to clean up the bound, and to get a much more interpretable theorem. And I guess like kind of the bad case here is like if h of m, the shattering coefficient is 2 to the m. In other words, I can, the maximum number of points I can label in all possible ways of concepts from the concept space is 2 to the m, then this bound is meaningless. Now, it turns out actually that intuitively speaking, the VC dimension is exactly roughly the point, the VC dimension of a concept space H is exactly roughly the point at which H stops looking like it contains all the functions. So then it's not exponential, h of m is not really exponential, it's only polynomial. And so then there is hope to solve for this inequality and to get a meaningful bound. Okay, this is at a high level, the intuition now. And so, right, it turns out that the VC dimension, one can show, but yeah, this Sauer's lemma that will tell us that the VC dimension of the hypothesis space, for the VC dimension of hypothesis space H, so we can show that this shattering coefficient h of m is, roughly speaking, m to the power of the VC dimension. And so then this inequality, if I plug this, if I combine the bound that contains the shattering coefficient, this first part of the bound, with the Sauer's lemma, then I get a nice kind of bound in the end. Okay, let me go through this a little bit more slowly. So I'm now gonna go and slowly define what VC dimension is. So what is a BC dimension? So basically, as I already mentioned, so we say that a set of classifiers H shatters a set of points S if basically all possible labelings of H, all possible labelings of S are achievable with classifiers from H. So what are all the possible, we have 2 to the size of S possible labelings for the set S using binary functions. And so I'm going to say that H shatters my set S if I can label S in all 2 to the size of S possible ways by using classifiers in H. Okay, this is what the shattering means. And what is the BC dimension of hypothesis space H? It's just the cardinality of the largest set S that can be shattered by H. Okay, if this is finite, and then if arbitrary large finite set can be shattered by H, then the BC dimension of H is infinite. Okay, so again, the BC dimension of hypothesis space H is just the cardinality of the largest set S that can be shattered by H. And if arbitrary large finite sets can be shattered by H, then the BC dimension is infinite. And so to show that the BC dimension of a hypothesis space H is D, what we need to show is that there exists a set of D points that can be shattered, that can be labeled in all possible ways using classifiers from H. And we also need to show that there is no set of D+1 points that can be shattered. Yeah, so that's just the definition of the BC dimension. And if H is finite, then you can easily show that the BC dimension is log size of H as one example. As another example here, because I'm trying to give a few examples what the BC dimension might look like. So for example, if we're considering the class of thresholds on the real line, which is a class we looked at earlier, when the BC dimension of H is 1. Why? Because you can easily show, you can label, there exists a base, there is one point that you can label that point in all possible ways by using thresholds. You can label that point both plus and minus using thresholds, depending where you put the threshold. But you can show that there is no set of 2 points that can be labeled in all possible ways using thresholds. So in particular, for example, for any 2 points that are distinct, this is one labeling I cannot achieve. I cannot label this point as plus and the point is right as minus. Right, so BC dimension of thresholds on the real line is 1. BC dimension of, you can show that the BC dimension of intervals on the real line is 2. Why? Because you can show, well, I can label any 2 points. You can quickly show, easily show that I can label any 2 points by using, I guess, you can label any 2 points in all possible ways, in all possible 4 ways by using intervals. But then you can show that no set of 3 points can be labeled in all possible ways by using intervals. In particular, if I put down any set of 3 points, say that my 3 points here are distinct, that's a harder case. There will be at least, there will be one labeling here, this specific labeling here, that cannot be achieved with intervals. So I can never label these 3 points in this way, plus, minus, plus. There is no way for me to label it using intervals, to achieve this labeling using intervals. So in this proof that the BC dimension of intervals on the real line is 2. And there are some other examples we can skip in the interest of time here. So let me actually keep one more example here. So the BC dimension, this is more relevant, I guess, because linear separators do appear in the real world. So if I'm looking at linear separators in R2, turns out that we can prove that the BC dimension is 3. How do we prove? Well, just you can show that if you put down 3 points that in a triangle like this, you can label all of them in all possible ways, in all possible 8 ways by using linear separators. But you cannot easily also prove that no set of 4 points can be labeled in all possible ways by using linear separators. Right, the argument, for example, here being, or an insight of the argument being, if the points are in the general position, then if one point lies inside the triangle formed by the others, then I cannot achieve this labeling using linear separators. Why? Because I can never label this point as negative and all the points outside as positive using linear separators, right? Because this point lies inside the convex hull, inside of the triangle formed by the others. So if I label these 3 points as positive by using the linear separator, automatically this red point will also be labeled as positive. So this labeling is not achievable. So this is one case. And another case is, what if all the points, none of the points lies in the triangle formed by the others? So it means all of the points are on the convex hull, they are on the boundary. well, then again, here you can show labeling that is not achievable. So in particular, you cannot achieve this labeling where I label these 2 points as the diagonally opposite points as say negative and these other 2 diagonal opposite points as positive. So like a quick argument like this in 2 dimensions shows that the VC dimension of linear separator is 3. In general, if Ellen has time, she'll prove in the section, in the recitation section in the that she's doing, she'll prove that the VC dimension of linear separators in RD is D plus 1. Okay. So this notion of complexity is actually a nice notion that one can then use in our sample complexity bounds. And the remarkable fact, and that's again, this is non-trivial, it will take a lecture to prove it, but it's very interesting. So the remarkable fact about the VC dimension is that we have this Sauer's lemma inequality for it. So so we can prove the following fact. So we can prove that if D is the VC dimension of the concept space H. Now, of course, by definition, if for any number of samples M smaller than or equal to D, H of M is 2 to the M. So basically, you know, like if, right, so this is just by definition because the VC dimension is the cardinality of the largest set of points that can be shattered, that can be labeled in all possible ways. But the remarkable thing, and this was proven in the Sauer's lemma, is that if M, the number of samples is strictly greater than D, then the shattering coefficient H of M is only polynomial in M. So it's now M to the D. So it's the VC dimension is exactly the moment when the shattering coefficient transitions from being exponential, like in the first case here, to being polynomial, like in the second case here. So for any M strictly greater than D, H of M, the shattering coefficient, the maximum number of ways of labeling M points of concepts for my cosine space is only M to the D. And now, why is this interesting here? Because it's interesting because then that means I can now go and solve. So recall how I told you we can get a theorem like the first one that I have here, or I can replace log size of H with log of the shattering coefficient. And because when M is strictly greater than D, the H of M is M to the D, that means that I can now magically solve this inequality. I can basically find values of M for which this inequality is satisfied. And moreover, I can solve it in a nice closed form solution. And I can get a bound that looks very pretty right now. It looks like if M, the number of samples I see in the training phase is roughly speaking 1 over epsilon times the VC dimension of H times log 1 over epsilon, but that's sufficient so that with high probability I generalize in the realizable case. So this is a critical property of the kind of the Sauer's lemma is kind of the critical property of the VC dimension that basically allows me to then get kind of great, I mean, good bounds for a generalization here. So basically, to summarize, kind of at least conceptually, because there are very interesting mathematical technical details, the key steps on transitioning from the case on H is finite to the case on H is infinite are these 2 key steps. So the first one is, turns out actually I can replace size of H with the shattering coefficient, roughly speaking, which is what is the shattering coefficient is basically an effective number of hypotheses, the maximum number of ways of labeling M points with concepts from my concept space. So I can replace size of H with the shattering coefficient. That's the first key point. And then the second key point, you know, I can then further kind of clean up this bound by using the notion of VC dimension. And again, what's the VC dimension is the cardinality of the largest set of points that can be labeled in all possible ways of concepts from my concept space. And the key property of this VC dimension is that it's basically exactly the moment when the shattering coefficient stops from being it's exactly this moment D when the shattering coefficient transitions from being exponential to being polynomial. So for if M, the number of samples is greater than D, when the shattering coefficient, the maximum number of ways of labeling M points with concepts from my concept space is only M to the D. And so because of it, then we can clean up this first bound that involves the shattering coefficient and get a very, very clean bound that looks like this. If the number of samples I see in the training phase is only the VC dimension of H over epsilon times the log 1 of epsilon, that's sufficient so that with high probability, again, we generalize. And I have here the bound for the realizable case. You can get similar bounds for the agnostic case. But that's nice because now, you know, as you've seen, you know, VC dimension now can be computed for interesting concept spaces like linear separators, neural networks and so on. So it's something that a combinatorial quantity that you can compute, and then you get very, very clean bounds on how many samples you need to generalize. Okay, so I guess now this was quick. Any questions? So about, I guess, anything that I mentioned. I tried to also give a little bit of a story of how the Vis dimension comes into place. You know, the concept itself is a very clean combinatorial quantity. You know, it's just the maximum. What's the Vis dimension of a set of functions H is just the cardinality of the largest set of points that can be labeled in all possible ways with functions from our search space H. And then there's something, a very clean combinatorial quantity, but it's like a learning theoretic measure of complexity, you know, and then it can be nicely computed for kind of many concept spaces, and people have computed it for many concept spaces that are relevant to machine learning. Now, this is a data independent measure of complexity, and it turns out, this is the point of my slide here, it turns out that actually, you know, like if you want to be more refined, so this work, no matter what the fixed underlying distribution is, no matter what the search space is, like this bound holds. You know, people have, there is a long line of research in statistical learning theory where you get data dependent bounds. So what if your distribution is nice? What if your target function is nice? You know, and then there are bounds like based on radiomarker complexity and based on covering bounds. So there are more tighter bounds that lead to better generalization in certain cases. But, you know, the bounds that work in general, no matter what the hypothesis space H is, and no matter what the underlying distribution is, are based on the BC dimension.
Yeah, go ahead.
So there is a reference to a paper in the radiomarker complexity. Could you just go back so we could see the, and could you,
this is a survey here, right? This radiomarker complexity generalization bound is a survey.
So were you, okay. Oh, okay. Will you be talking a little bit about the radiomarker complexity or not?
I was not planning to talk about it because that next lecture I was planning to, I guess I'm out of time right now, but the next lecture I was planning to talk about active learning and distributed learning, is what I promised. Okay. You know, but I can, if I guess I can bring it up right now if you're interested. So it's really just at the high level, it's like the ability of the function class, so to fit noise. That's in a succinct way to describe what basically what the radiomarker complexity is. And then it turns out is a distribution dependent quantity, and it turns out that actually you get bounds based on the radiomarker complexity, but then you can always upper bound radiomarker complexity as a function of the BC dimension. And so you can, if you prove the bounds based on radiomarker complexity, you can recover the bounds for based on BC dimension. So it was a notion introduced later on, compared to the, I guess what I talked about today is from the 70s, really, from, I guess, yeah, from Babnik and Chervonenkis. Radiomarker complexity is introduced later on. In the case one, I guess for the case of binary classifiers, you can, once you prove the radiomarker complexity based bounds, you can recover the BC dimension based bounds. Actually, if you are curious, I have some extra slides. I was initially thinking to talk about it, but then I decided not to. Let me bring them. If you're just curious, the math becomes more complicated and so that's why I decided not to present them today. And also, I guess I'm also out of time at this moment, but if you're curious, since you asked the question, I do have how it looks like on the slide.
Okay, we should probably take the break now so we can move on. So,
okay. I guess you'll share your slides, Nina, at some point.
Yeah, I'll share my slides, and if you're curious, exactly, it becomes more complex. If you're curious, I'll have to, yeah, I'll share the slides and you can look on the slides, and I guess I'm happy to take questions. It's intuitively, it's a very, very simple noise. It's just the ability of the concept class to capture noise, but you know, once you put that, I mean, to put down the math and to go through it requires some minutes, you know, to think about what it means and so on.
So we're getting
so I guess maybe I'm not going to go through it right now. If you're curious, I'll share the slides. Yeah.
We're gonna give again 10 minutes. We